In this video, I'll be showing you guys and explaining all the axioms you need to know for your discrete math course to do your proofs. If you don't know what an axiom is, they're just facts that you assume to be true at the beginning of a proof. Because when you are doing proofs, you're going to prove very simple things. Like, for example, is 3 odd? Right? That could be an example of a proof that you might do at the beginning. And you need to know very simple things, the very definitions of odd, prime, composite, in order to be able to prove these things. And you can use very simple things called axioms to prove them. So, we're going to cover arithmetic properties in this video, divisibility and modular arithmetic, and also a couple things on prime and composite numbers. So, let's go ahead and talk about arithmetic properties first. So this right here is the list of all the equalities and arithmetic properties you need to know. Some of them might seem silly, like this one, a is equal to a. Well, that's pretty obvious, right? But in your proofs, you're going to be proving pretty obvious things sometimes, okay? And if you want to prove obvious things, you need to prove even more. You need to use even more obvious assumptions. And these obvious axioms are quite useful depending on the rigor and strictness of the proofs in your class. Now, most discrete math courses that are, freshman or sophomore level, they're probably not going to make you use these. These are implied, basically, right? A is equal to A. That's kind of implied. But if you go to a higher level proof course, they'll probably, especially if you're a math major, they'll probably make you have to write these things down. But who knows? I'm not a math major. I'm just here to teach what I learned in my classes. So the first one, a is equal to a, right? If you have some number assigned to a variable a, it's equal to a, right? That's very obvious. We also have this, a is equal to b, b is also equal to a, okay? Right? If a is equal to b, b is also equal to a. And the names of these properties are, this one is the reflexive property, and this right is the symmetric property, okay? And don't let the symmetric bleed into the other identities. This right here is if a is equal to b and b is equal to c, a is also equal to c. This right here is called the transitive. All right, we have a plus 0 is equal to a. Pretty obvious, right? If you add 0 to a number, you get the same number. And how about this one? Well, if you have any number, complex, real, integer, rational, who cares? If you add the negative of that number to itself, you get 0. Right? And you could try this with complex numbers if you are familiar with complex numbers. You still get 0, okay? And here's the thing. These are all the, additive ones. This is kind of equalities. This right here is addition. Well, the thing about addition is that the cumulative, associative laws, they still apply, all right? So, again, depending on the rigor of your course, they're going to make you state by the definition of cumulative property, you could do this in your proof, right? They might make you say that. Very tedious, but most of the time in my class I just write down by using some algebra in my proofs, and then I got a good score on my exam. But this next one, multiplication, a times 1 is equal to a. Okay, makes sense. A times 0 is equal to 0, right? Any number a, right, real, complex, doesn't matter, times 0 should be equal to 0. All right, distributive property as well. They might make you say, I'm using the distributive property here, and then you do the distributive property. So make sure you know how the commutative, associative, and distributive properties work for both multiplication and addition. These are the simple ones. Let's move on to ones that are a little less obvious. So we have the divisibility and the modular axioms. And these right here at the bottom, I'll explain them later, okay? And they're actually less important, and I'll show you why. But this right here stands for divisible by. So this line means A is divisible by B. So let's say 25 was A, all right? And B was 5. Is A divisible by B? Is 25 divisible by 5? Well, it is, because if we divide 25 by 5, we actually get an integer. Therefore, it is divisible. Key word, integer. In order for a number to be divisible by another number, it must result in an integer when you divide them. So 25 over 5 results in an integer. How about this? What if b was equal to 4? What if b was equal to 4? Is 25 divisible by 4? It's not. You get a decimal. And a decimal, or a rational number, sorry, not a rational number, a number that isn't an integer, let's say that. A number that isn't an integer, as a result of dividing them, means that they are not divisible, all right? And That's important to note. But here's the thing about this. You can express it as an equality. And this actually makes sense. You can express it as an equality. So if we have a number a, we have a number b, that means if they are divisible, it means that there's an integer k such that if we multiply k by b, we can get a. Okay? In the case of 25 and 5, for a and b, k is just another 5. And 5 times 5 is equal to 25, right? B times k is equal to 25. So this right here, if you see this in any of your proofs, you kind of want to move it to the equality immediately. You want to do this as fast as you can because you can't really do much with this. I'm not going to lie. You cannot do much with this. But with an equality, you can work with algebra and, I don't know, numbers. You could do things with equality. You could do things with numbers, okay? And algebra is the key for a lot of these proofs. Okay, how about this right here? All right, A is modularly equivalent to B. Okay, this means they're modularly equivalent. So if you take the mod of the same n on A and the same n on B, then they should be equivalent. So if you don't know what mod does, I have a video on that. I'll put the link down in the description. But let's show you this. You can write this down in another notation too. I just wanted to express that. N underneath the triple equal sign, right? This can be expressed in the same way. My class just like doing it like this, so I'm doing it like this. But this means that they're modularly equivalent. So if you take the mod of both of these integers, a and b, then they should be the same thing, okay? With the same number that you're taking the mod of. Here's the thing about this. You can actually express this guy, and again, this guy isn't very helpful. Thing I underlined, this is not very helpful in your proofs. You can't really do algebra with this, right? But you could do algebra with this. You get the divisibility. And with divisibility, you could turn it into an algebraic statement. You could turn it into equality. So this right here is very helpful, okay? So if you see a module like this, you kind of want to turn to this form, and with the divisibility, you want to turn to this form. All right? But basically, n is divisible by b minus a. B minus a. And again, these can be flipped around. So n could be a minus b, and that's because divisibility is independent from the negative numbers. Okay, so even if you have a minus b, you get a negative number compared to b minus a, you'll get the same result for divisibility. All right. So these two, divisibility and modular identity axiom. If you get this, you should turn it to the divisibility, and you should turn it to the equality as quickly as you can. Okay, you always want to turn things. The general word of advice: you want to turn things to equalities as fast as you can, unless you have some other axioms or things that you want to prove. But let's take a look at this. Why did I separate these down here? The reason why I separate these down here is because you can prove all of them. And these might be things you have to prove. There might not be axioms. Okay, you can prove all of them with the divisibility rules. You can prove all of them with the divisibility rules. So actually take a look at these, because I'm not gonna lie, I got one of these problems. I got one of these proofs on one of my problem sets. So this might show up in your class, a discrete math course, but I'll explain them anyways if they're actually axioms in your course. Basically, if a is divisible by b and a is divisible by c, a is also divisible by b plus c. Okay, if a is divisible by b, and then a is divisible by b for any integer if you multiply by any integer. So let's not use c, because c might be a little confusing actually. But if a is divisible by b and you multiply b by just some random integer, does not matter what integer, a will still be divisible by bk. Okay, this will hold true. Okay, so how about this? A is divisible by b and b is divisible by c, then a is also divisible by c. So these are a couple of the rules, but remember, these down here might actually be things you have to prove, not axioms. Keep that in mind. This is the second to last section. Let's define an even number. An even number is just any number that can be expressed as 2 times another integer. So let's say, let's prove that 4 is an even number. Well, 4 is an even number because it can be expressed as 2 times an integer, k, and that integer k is equal to 2, right? All right, how about this? Is 6 an even number? Well, can 6 be expressed as 2 times the integer? It can. When k is equal to 3, an integer, and you multiply by 2, you get 6. Therefore, 6 is an even number. So these right here are the cream of the crop. You will use these a lot in your discrete math course because they're pretty simple to make proofs from, and they're easy to understand. Okay, so even, odd, rational, really get the hang of these definitions. All right. How about odd? What's odd? Well, odd is any number that can be expressed as 2 times some integer. Keep in mind integer. All right. Anything that's not an integer, this does not apply. This rule does not apply to. But 2 times an integer plus 1 is equal to the odd number. Okay. How about 1? Is 1 an odd number? Well, can we express it as 2 times an integer plus 1? Yeah. When k is equal to 0, 1 is equal to 1, right? Because 0 cancels out this 2 right here. So this is true, right? So 1 is an odd number. I just proved that to you right now. And if you're curious, 0 is even. It's considered even because you cannot express 0 as 2k plus 1, right? That's just impossible. There's no integer k that you can choose to get to 0 on that equation. But let's move on. How about rational numbers? When you're doing things related to irrational or rational numbers, it's very convenient to know that a rational number is just any time you have an integer over an integer. So if you can express a number c as an integer over an integer, that's a rational number. And here's the thing, 3 is a rational number because you can express 3 as 3 over 1. These are 2 integers over an integer. Keep in mind, again, these have to be integers. A and B have to be integers, just like how k has to be an integer. All right, they cannot be non-integers. I'm trying not to say rational because 3 over 1 is also rational, and it's an integer. So, but you know what I mean, right? Rational means a fraction, like 4 over 3, right? This cannot be expressed as an integer. But 3 can be defined as a rational number, 3 over 1. So remember, rational just means that if you can express this rational number as an integer over an integer. Let's move on to the last section, prime and composites. So, what is a prime number? Well, a prime number is if a number is divisible only by 1 in itself. Okay, so for example, 7 has no factors besides 7 and 1. Right? So 1 and itself. 7 is a prime number. How about 9? Is 9 a prime number? 9 is not a prime number because 9 can be divided by 1, but 9 can also be divided by 3. All right? So it's not a prime number. It's a composite number. That's the opposite of prime. But keep in mind, 1 is neither prime nor composite. And that is because 1 only has one factor, itself. Okay, so it's not considered prime or composite. That's why I specifically wrote down a has to be greater than 1. And keep in mind, a is an integer in this case. All right, so any integer greater than 1 that is divisible by only 1 in itself is prime. All right, and composite is just the exact opposite. Composite just means that has more than 2 factors. Okay, and again, has to be an integer greater than 1. All right, so example of composite, 10. Right? It can be divisible by 10 and it's 10 and 1, right? 10 is divisible by 10 and by 1. But 10 is also divisible by 5 and 2. Right? 10 divided by 5 is equal to 2. 10 divided by 2 is equal to 5. So it's divisible. So composite, just any number that's not prime, besides 1 and besides 0, of course. Sorry, I lied. I lied a little bit. And the last thing, and this one's quick, last thing I'd like to cover is that when you add and subtract or multiply integers, all right, you also get another integer. Now, keep in mind, I didn't say divide, and that's for a very good reason. Let's say divide 5 by 3. This is not an integer, right? This is like 1.6 repeating. Okay, so dividing doesn't apply to this, but if you add, subtract, and multiply integers, this should result in another integer. All right, this is very important, and this one is actually quite useful when you're proving if something is even or odd. So it might not seem very direct, but this one keep that in mind and mention it and state it inside of your proofs. You can't just assume things are integers, right? Or you can't just imply it without saying it. But anyways, if you have any questions, put it down in your comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching. 530 subs. Oh yeah. Wait till 1K. Bro, if I hit 1K subs, I don't even know. I'm gonna punch my desk